Throughout this training, or at any time you need support, there are many ways to contact us. You can follow us on all major social media platforms or email us directly via our website, or you can click the Cancel Connect icon shown at the bottom of this slide on our website to book a consultation with one of our experts.
A histogram is a graphical representation of a frequency distribution of continuous data. The data is divided into class intervals or bins and are noted by rectangles. The rectangles are on the x-axis. The y-axis plots the frequencies of the data. Each rectangle represents the number of frequencies that lie within that particular class of intervals.
One of the greatest benefits of the histogram is that we can visualize the spread of our data and not just rely on the average. So what's the trouble with averages?
Everything.
They hide the spread. And it's really easy to miss important information about the reality of a process when we only pay attention to the nice, smoothed out average. Here, we'll explore a bit more about analyzing a histogram. First, let's do a refresher on the class intervals, or the bins. A histogram displays numerical data by grouping the data into bins of equal width. Each bin is plotted as a bar, whose height corresponds to how many data points are in that bin. Bins are also sometimes called intervals, or classes, or buckets, and there's no strict rule on how many bins to use. We just try to avoid using too few or too many bins. In the Cancel templates are some guidelines for selecting the right bin size.
So the general rule, which is in your workbook, is to first count the number of data points. Then calculate the number of bins by taking the square root of the number of data points and round up. Lastly, calculate the bin width by dividing the specification tolerance or range, that is the USL minus the LSL, or max minus the min value, by the number of bins.
The most recognized shape of a histogram is the bell curve, also known as the normal distribution. As we've learned, the great thing about the normal distribution is that we can draw solid conclusions using the pattern of data in the normal distribution. We know that approximately 68% of our data points will be around the center, at plus or minus 1 standard deviation, and that less data will be in the next cut of standard deviation, that's our plus or minus 2 sigmas, and then there's that last bit that will predictably fall near the high and the low data points. And we can predict that 99.7% of data points will fall within this range. This pattern is what's used to detect special cause patterns in our run chart and our control chart. We know that if we suddenly have a huge chunk of data all in a row way out there in the far right tail, that something's up.
Normally, distributed data has a symmetric distribution, one where the left and the right-hand sides on the distribution are roughly equally balanced around the mean. Since the box plot and the histogram show distributions, we can observe the type of distribution using both. The histogram here shows a typical symmetric distribution. Another property of a symmetric distribution is that its median is in the middle. For symmetric distributions, the mean is approximately equal to the median and the mode. The tails of the distribution are the parts to the left and to the right, away from the mean. The tail is the part where the counts in the histogram become smaller. For a symmetric distribution, the left and right tails are equally balanced, meaning that they have about the same length. The normal distribution. It is unimodal, meaning that it has one peak. Statistical tests, including special cause patterns, assume that our data is normally distributed. If the left side of the histogram resembles a mirror image of the right, then the data are said to be symmetric. In this case, the mean, or the average, is a good approximation for the center of the data, and we can therefore safely use statistical tools that use the mean to analyze our data.
But don't expect symmetric data to have an exact and perfect shape. Data hardly ever falls into perfect patterns. So without using advanced stats, you have to decide whether the data shape is close enough to be called symmetric. If the differences aren't significant enough, you can classify it as symmetric or roughly symmetric. Otherwise, you can classify the data as non-symmetric.
I always can, baby. Go, just go, go.
Okay. If the data is not symmetric, then it's either left skewed or right skewed. With skewed data, the mean or the average may not provide a good estimate for the center of the data. It doesn't do a good job of representing where most of the data falls. In this case, we may choose to use the median to evaluate the center of the data rather than the mean.
A distribution that is skewed to the left, also called a negatively skewed histogram, has a peak to the right of the center, more gradually tapering to the left side. If the data is left skewed with a tail out to the left, the mean is typically less than the median. A right skewed histogram, also called a positively skewed histogram, has a peak that is left of center and a more gradual tapering to the right side of the graph. If the data is right skewed with a tail out to the right, the mean is typically greater than the median.
Think about a business meeting. If we were to plot how many minutes before the meeting people arrived, we'd likely see a left skew. 1 or 2 people show up early, then the closer it gets to the meeting time, more and more people show up, with the majority of people showing up right at the meeting start time. We'd expect to see the exact opposite when the meeting ends. Most people leave very quickly with a few stragglers who are hanging around chatting. Just remember, a skewed distribution is not good or bad, it just indicates how the process works.
In a skewed distribution, we know that the data is not symmetric. From the box and whisker diagram, we can see that the median is closer to the first quartile than the third quartile, and the right hand of the side of the tail of the distribution is longer than the left. For a skewed distribution, it's more complicated to estimate a typical value. If the distribution is symmetric, the typical value is clear. There is a well-defined center of the distribution. For example, for a bell-shaped symmetric distribution, and the mean, median and the mode are all right around the same value. For a skewed distribution, however, there is no center in the usual sense of the word. Depending on how skewed the distribution is, we can use the mean, the median, or the mode to represent the center or the typical value. And usually using all three is very, very helpful. The fact that they are not similar, as they are in a normal distribution, gives us important information about our process.
We've been talking about the center or the typical value in a histogram using the mean, median, or mode. The mode being the highest peak. A bimodal pattern means that there are 2 peaks. The peaks and the data under each peak may or may not be symmetric. For example, let's say that we measure the height of all the employees of a large company. In the example shown here, there's a peak around 42 or so and a peak around 58 or so. It's almost as if 2 symmetrical bell-shaped histograms were shoved together. There would be a peak around the typical height of a man and a peak around the typical height of a woman. That's because, just like a bimodal usually suggests, we have 2 different groups in our data. In our height example, we'd expect to see 2 modes because of the differences in height between men and women. We might be measuring order delivery time and have both online and in-person customers in one histogram. Typically, it's best to split the groups apart so they can be studied individually, or to put the data on a box plot so they can be easily compared. One other example of a bimodal histogram is when we have a before and after data in one big fat chart. If our project was focused on reducing cycle time, we might expect to see a bimodal chart if we included all the data from before the improvement and after the improvement in one histogram. That is, if we were successful.
Outliers are one type of special cause that can be identified on a control chart, and outliers can also be seen on a histogram. Outliers are extremely low or high values that do not fall near any of the other data points. Sometimes outliers represent special causes or it may be the high end of a predictable range, especially if we have fewer than 30 data points on our histogram. Whatever the case may be, outliers should not be ignored or deleted. They should be analyzed as they can shed interesting information about your data.
Another less common pattern is the uniform distribution. This means that the data has no high or low frequencies of data points. The data is evenly distributed across all values. This pattern is really unusual, and it usually means that the wrong chart was used, or there's some problem with the data. For example, this type of data might be seen if we're using categorical or discrete data instead of continuous data, which is required for a histogram.
Bringing the histogram back to our projects, keep in mind that our center and our spreads are only meaningful when compared to the requirements, also called the specification or spec limits. We might not be focused on changing the average. Maybe we're focused on reducing variation so that our results consistently and predictably fall within customer requirements.
In order to reduce the variation, we have to understand the different factors that cause our results to be high and low. And one of the questions is, does time or sequence have any impact on the highs and lows? For example, let's say that this histogram is measuring how quickly a phone call is resolved. That would mean that our measure along the x-axis is something like minutes, and the left side is low minutes, that means fast, and the right side is high minutes, or it's slow. We might have a hypothesis that over the last month, we've gotten a lot faster as the call center reps have gone through the learning curve. That means that the hypothesis that the slow calls, the ones on the right side of the chart, would have happened earlier in the process. So how can we test this hypothesis? Since a histogram is a snapshot in time, it doesn't show the data over time or across time. For that, we need a run chart or a control chart. If the hypothesis is correct, we would expect to see a downward trend over time, showing that the calls were getting quicker as time went on. A histogram and a run chart work really well together for this reason.
And here's your handy one-point lesson for the histogram. Again, lots of information on this one page. You don't have to commit it all to your memory, but you have to know that the tool exists and when to use it. Then you'll be able to grab the one-point lesson for a quick refresher and get back to your analysis. It has been our sincere pleasure being with you through this part of the training, and we thank you for your dedication to creating a better workplace and an environment that you can truly enjoy.